Okay, in this video, let's talk about the section 5.3. The graph of a rational function. We already know how to graph a polynomial function. Now let's talk about the graph of a rational function. Okay, we will have several examples. The first example is about this rational function. R of x is equal to x minus 1 over x squared minus 4. First, let's determine the domain. In order to determine the domain, we need the zeros of the denominator and remove those zeros. So we factor the denominator. So here we use the property x squared minus a squared is equal to x minus a times x plus a. So after we factor out the denominator, we can see that the domain of R of x is the set of everything, the set of all real numbers except 2 and negative 2. Okay, x cannot be equal to 2, x cannot be equal to negative 2. So this is step 1. And step 2, we check that you cannot cancel any terms. In other words, the numerator and the denominator have no common factors. So R of x is in lowest term. Lowest terms. Okay, lowest, sorry, not lowest, lowest term. Okay, step 3. Once the rational function is in lowest term, we can determine the intercepts. Okay, so the intercepts, y-intercept. Y-intercept R of 0. 0 is in the domain, so it has a y-intercept. R of 0, x is equal to 0. The numerator 0 minus 1 is negative 1. Here, 0 minus 1, negative 1. 0 squared minus 4 is negative 4. Whatever. I plug in here, I will get same thing. So the y-intercept is 1 over 4. The numerator is negative 1. Denominator is negative 4. Okay. The x-intercept. X-intercept is a solution of R of x equal to 0. In other words, the numerator is equal to 0. So x is equal to 1. This is a x-intercept. Okay. So there's only one x-intercept. And after you get this x-intercept, let's study the behavior near the x-intercept. Near 1. Near 1, R of x is approximately 1 comes from x minus 1, so you keep x minus 1. And you replace x by 1 in other terms. So here you will use 1. 1 squared is 1 minus 4. So it's negative 1 over 3 x minus 1. So when x is close to 1, it is a slope. It is a linear function with a negative slope. So it looks like this. Negative slope is heading to the northwest. Okay. Okay. So this is the behavior near the intercept. X-intercept. Okay, so step 4. We locate the vertical asymptotes. The vertical asymptote comes from the zeros of the denominator when you have lowest term. So the zeros of denominator is -2 and +2. So x equal to 2, x equal to -2 are vertical asymptote. Okay, so this is a vertical asymptote. And then let's this is a step 4, and step 5. Let's determine the horizontal asymptote or the oblique asymptote. And we know that the graph of a rational function can never intersect vertical asymptote, but the graph of a rational function may intersect horizontal or oblique asymptote. So first, this rational function is proper. So y equal to 0 is horizontal asymptote. Okay, so a proper rational function has horizontal asymptote y equal to 0. And you set this rational function equal to this number, equal to this horizontal asymptote 0. You get x minus 1 equal to 0, so x equal to 1. So this is the intersection, the x coordinate of the intersection point. So 1, x equal to 1, the graph of Rx intersect the line y equal to 0. Okay, because they equal to each other. Okay, so this is the possible intersection of a graph of a rational function with a horizontal asymptote. This is a unique possible point. And the graph of a rational function can never intersect vertical asymptote. Okay, that's all the steps we have so far. We have more steps. So in the first step, we determine the domain. Second step, we make sure it is in the lowest term. And third step, we get x-intercept, y-intercept. And we also study the behavior near x-intercept. And fourth step, we get vertical asymptotes. There are two vertical asymptotes. And step 5, we get either horizontal or oblique asymptote based on the rational function. This is a proper, so the horizontal asymptote is 0. And we also find the possible intersection point between the graph and the horizontal asymptote. So that's what we just did in the first 5 steps. Step 6, we use the zeros of the numerator and the denominator to divide, you see, the zeros of numerator, 1. The zeros of denominator, -2, +2. So you have -2, 1, 2. And then you have, you see, 1, 2, 3, 4. You have four parts. On 4 different intervals, you pick up sample point. On 4 different subintervals, you pick up sample point. For example, here you pick up 3. X will be selected to be 3. And here we may pick up 0. And here we pick up 3 halves. Here we pick up 3. We pick up sample point, and then we evaluate R of x. So here's R of a -3. R of a -3, let's check. -3 minus 1 is -4. -3 squared is 9, minus 4 is 5. So it's -4 over 5. Okay? And then you check R of a 0. R of a 0, we just did it. R of 0 is 1 over 4. And then we check R over 3/2. Sorry, it's a small. R over 3/2. R over 3/2, if you do the computation, it's a -2/7. It's -2/7. And then we have R over 3. R over 3 is what? It's 2/5. Okay, so we have the evaluation. The evaluation tells us over the corresponding subintervals, the graph will be either below the x-axis or above x-axis. Okay, so here it means the graph below x-axis. Here is above. Here is below. Here is above. Below or above, it just depends on the sign. The value is not extremely important. Okay, and then this is x value, this is y value. You can get the point on the graph. And step 7, that's a step 6. And step 7, we will study the behavior of the graph near the asymptote. So where's the asymptote? Asymptote, there are several steps. First, y equal to 0 is the horizontal asymptote. Horizontal asymptote, and when x is less than -2, you see, this is the x-axis, this is x-axis. X equal to 0 is the x-axis. So for x less than -2, the graph is below y equal to 0. And then for the corresponding interval, you will see one is above, one is below, one is above, one is below. Okay? So that's the relative positions. And second, the vertical asymptote. X equal to -2. X equal to -2 is here. Then you have two sides. For example, let's pick up a point, -3. For left side, the graph will what? Will approach to negative part. Right side will approach the right part. So it's like this way. Okay? So left side, R over -3. Is negative. And if you want a detailed description, it looks like this. Negative part of -2. Yes, negative part of -2. Let's see, if, for example, x is -2.01. -2.01. Then x squared minus 4 is almost 0. But x minus 1 is -2.01 minus 1 is -3.01. This is 0, but it's always greater than 0. X squared is a -2.01. It's a greater than 4. So this is approaches 0, but positive. So a negative number over a positive 0, this will approaches -infinity on the left side. Okay? So left side, it goes to -infinity. And right side, for example, you pick up x is equal to -1.99. X is -1.99. X squared is less than 4. But x squared minus 4 goes to 0. Very close. Negative, the difference is negative, but close to 0. And the numerator, -1.99 minus -1, the numerator is -2.99. It's a negative number over a negative number, it's a positive. Okay? So it's a very subtle study. So on right side is positive, left side is negative. Okay, so that's a study of the behavior close to this vertical asymptote. Let's study the behavior close to the other vertical asymptote. We will repeat this process. This is a good exercise. Left side. What is left side? Left side of 2, we pick up x equal to 1.99. Right, very close to 2, but from left side is less than 2. So x squared is less than 4. 4 is 2 squared, of course it's less than. And x squared minus 4 is less than 0. Since x is close to 2, so difference is close to 0. So the difference is 0. And numerator, this time the numerator, x minus 1 is 0.99. It's a positive number. A positive number over a negative number is negative infinity. Positive over negative is negative infinity. And right side, we choose 2.01. Right side of 2.01. Then x squared is greater than 4. So x squared minus 4 is greater than 0. And x squared minus 4 approaches 0. Very close, tiny. And x minus 1 is 1.01. It is positive. You have a positive over positive. It's positive infinity. It's positive. Here is a positive over negative. It's negative infinity. Here is the same thing. So you see, x squared is greater than 4. X squared minus 4 is greater than 0. So you get a negative number over a positive number. That's why you get a negative infinity. You get a negative number over negative 0. You get a positive infinity. Sorry. We should write it this way. We should write this way. Okay. Keep this in mind. This is the first example. A lot of information will be new for us. Okay, now we are going to collect all 7 steps together and try to sketch it. Okay, let's see how do we sketch. First, it has a 2 vertical asymptote, -2 and +2. You draw a dotted line to demonstrate vertical asymptote. And there's a x-intercept 1. At x-intercept 1, it behaves like a straight line with negative slope, so it's this way. And let's check. When you have -2, on the left side, it approaches negative infinity, this way. Don't cross it. It's negative infinity. On the right side, it approaches positive infinity. For the 2, on the left side, it approaches negative infinity. Right side approaches positive infinity. Okay, at infinity, negative infinity approaches 0. Right infinity, it also approaches 0. Here, you see, I draw it below the x-axis because when it is less than -2, it's always below the x-axis. You have to draw it this way. And here's above x-axis because this is above x-axis. And then you just connect them. Connect them smoothly. Yeah. There's no other way to sketch it. And don't make a wave. For the rational function, polynomial function, the graph will never wave randomly. Okay? Whenever there is a wave, there's some reasons behind it. Now we don't discuss reason means there's no such wave. Okay? So you see here, that's the steps. First, we just label the possible sketch and then we try to connect them. If you are not extremely sure about the connection, you just randomly pick up some extra supporting point to determine the relative. For example, you can pick up -1 and determine the value, and you can pick up other stuff and determine different value. Those are the supporting sample point. Okay, so this is a first example. It's also very comprehensive, complex. So go over this example and make sure you understand it. And you don't have to worry about steps. if you have some similar problem in the exam, I will literally write down the step and ask you to do what you need to do in that step. For example, I will put step 1, say, find the domain. And step 2, say, is this in the lowest terms? Or step 3, what is a vertical asymptote and a horizontal asymptote? Something like that. I will make the question more concrete, not like this. This is an example. Okay? Okay, let's do more example. X squared minus 1 over x. So first of all, domain. Domain is the set of all real numbers except x equal to 0, because when x is 0, the denominator is 0. It's undefined. Okay, this is domain. And step 2, it is in the lowest term, because this one, if you factor it, it's x minus 1 times x plus 1 over x. You cannot cancel any terms, so r is in lowest terms. And step 3, the intercept. And because 0 is not in the domain, there is no y-intercept. No y-intercept. X-intercept, you let r of x equal to 0, which implies x minus 1, x plus 1. The numerator is equal to 0, so you get x equal to 1, x equal to negative 1. There are two x-intercepts. There are two x-intercepts. And then you will have to study the behavior near 1 and near negative 1. Near 1, r of x is almost, okay, 1 comes from x minus 1, so you keep this x minus 1 term. And 1 plus 1 is 2 over 1. In rest of the terms, you just replace x by 1. So it is 2 times x minus 1. So near number 1, the graph of a rational function is almost a linear function, 2 times x minus 1. Near negative 1 comes from x plus 1. So you get x plus 1. And then here you use negative 1. Negative 1 minus 1 is negative 2 over negative 1. So it's a 2x plus 1. It's also a linear function with a slope 2. Okay, this is a behavior near the x-intercept. And step 4, vertical asymptote. There's only one vertical asymptote. X equal to 0 is a vertical asymptote. Okay, step 5. Horizontal or oblique asymptote. Horizontal oblique. This one you have to do the long division. So you divide x squared by x, you get x. So the rational function is equal to x plus negative 1 over x. Okay, so we get y equal to x. This part is the oblique asymptote. It's oblique asymptote. Okay, when after we have oblique asymptote, we have to check if this oblique asymptote intersects the graph or not. So you set this r of x equal to x, this x, and you try to compute it. So get x squared minus 1 over x equal to x. So x squared minus 1 is x squared, you move this x to the right side, so you get a -1 equal to 0. Impossible, no solution. This has no solution, it means the graph of r of x does not intersect the oblique asymptote. Does not intersect the line y equal to x. Okay? If you find the solution, that is the intersection point. If you do not find the solution, it means they don't intersect. Okay? And then let's check. In the number line, we have 0, -1, and +1. So you have 1, 2, 3, 4. You have 4 regions. Over those 4 regions, you're going to pick up sample point. For example, here. You pick up -2. Here you pick up -1/2, +1/2, +2. And then you're going to evaluate r of -2 based on the definition. R of -2 is a -3/2. R of -1/2 is a 3/2. R of 1/2 is -3/2. R of 2 is 3/2. Okay, so what after you get this, you can see that this is below x-axis, above x-axis, below x-axis, above x-axis. Okay, so that's the information we have. Okay, this is a step 6. In step 6, we are trying to determine roughly the relative position between the graph and the x-axis. And next to it, we are going to study the behavior on the either oblique asymptote or the vertical asymptote. Okay, so because this part, it is always below the x-axis, and this part is always above x-axis, and the graph does not intersect the oblique asymptote. Okay, so what we can say, we have the following stuff, and so this is one thing. The graph does not intersect the oblique asymptote, and for the vertical asymptote, x equal to 0. Where's vertical asymptote? Here, x equal to 0. The left side, let's check. The left side, x, let's pick up -0.1. -0.1. Then r of -0.1 is, you see, -0.1 squared is 0.01 minus 1 over 0.01. So what it is, it's a -0.99 over 0.01. This is a 0. You consider this as 0, negative. So it's a positive infinity. It's a positive infinity. So this denominator will be considered as 0 because the denominator is close to 0. And numerator, you get a number. Numerator, you try to determine the sign. For the numerator, we are interested in the sign. For the denominator, we are also interested in the sign, plus it has to be 0. If you have a minus, it's plus, so it's going to be positive infinity. The right side, let's see, r of 0.1. Right side x is 0.1. Then it is 0.01 a square. Remember, you have square, so this is 0.01 minus 1, and denominator is 0, 1. Denominator is x, so x is 0. That's my bad here. There's no second 0. It's just 1, 0.1. So it is a 0.99 negative over 0.1. Okay, this is 0. This is negative. A negative number over no sign. So it's a negative number over 0 is negative infinity. This is a negative number over another negative number 0, another negative 0. This is negative 0. So you will get a positive infinity. Okay, so this is a positive infinity, this is negative infinity. Let's try to get everything. Let's see how I did it. Vertical asymptote, y-axis, x equal to 0. This is vertical asymptote. Horizontal asymptote, y equal to x. And it has two zeros, negative 1, positive 1, negative 1, positive 1. When x approaches infinity or negative infinity, the graph will be close to the oblique asymptote. And since the point is here, if you sketch any graph on this part, below it, you have to cross the oblique asymptote. If you cross it, there's the intersection point. Since this problem, there's no intersection point between the graph and the oblique asymptote, you cannot sketch the graph below the x-axis for the left part. You can only sketch it on top of a oblique asymptote. And also on the left side, you see it's a positive infinity. It's a positive infinity, so it's this way. Okay, so that's what we get. And similarly, you have 1 point on the graph here. And at infinity, the graph will be close to the oblique asymptote. You cannot sketch a graph above it, because if you do it above, you cross the oblique asymptote. So you can only sketch this way. And here, on the right side of 0, it approaches negative infinity. Okay, so that's it. That's a graph. Okay, so if the function is defined, is well defined between 0 and the negative infinity, this part is well defined, so the graph will be connected. Don't break it. Here, from 0 to positive infinity, it's also connected. Don't break it. This is, we call it continuous. Okay, so the difficult part, I believe, is in step 7. How do I know it's a positive infinity or negative infinity? When you get the step 7, the important thing is to determine the numerator, the sign of the numerator and the denominator. Close to the vertical asymptote, you will definitely have infinity. The only important thing is positive or negative. So you just plug in a number close to this vertical asymptote, either from left or from the right. And then you check the sign. If you get a positive number, it doesn't matter how big or how small it is, you get a positive number correctly, then it will be positive infinity. Here, if you get a negative number, it will be negative infinity. Okay? So that's the idea. Okay. Let's try to do more examples. We have more examples. So our rational function r of x is x to 4 plus 1 x squared. Step 1, domain. Domain is a set of all real numbers except x equal to 0. And step 2, it is in the lowest term. Lowest terms. Okay, and step 3. Because 0 is not in the domain, there is no y-intercept. For x-intercept, you set r of x equal to 0. It means enumerate x to 4 plus 1 equal to 0. This one has no solution. So there's no x-intercept. That's good. There's no x-intercept. We don't study the behavior near the x-intercept. So it saves a lot. Okay, and step 4, vertical asymptote. X equal to 0 is the vertical asymptote. And step 5, horizontal or oblique asymptote. And we notice that the difference of a degree, this is not proper, this is improper. The difference of a degrees is 2, so it has no oblique or the horizontal asymptote. But when I do the long division, you will get the rational function is equal to x squared plus 1 over x squared. So basically it means when x approaches positive negative infinity, the graph will be close to x squared. The graph is close to y equal to x squared as x approaches infinity or x approaches negative infinity. So even though we don't have straight line, but we know more or less the graph is like this. It will be like this, right? Okay, 5, 6. 6 is a summary, so 6. But it's okay, we only have one bad point. We don't have x-intercept, so we don't have a lot of small intervals. Okay, on the left side, let's pick up a -1. Right side, let's pick up +1. And we evaluate r of 1. R of 1, what is r of 1? R of 1 is 2. R of -1 is 2. R of 1 is also 2. Okay? And because they are 2, 2, it's above x-axis. This one is above x-axis. Okay? And step 7, the behavior close to the asymptote. Behavior close to asymptote. And the vertical asymptote, x equal to 0. The left side, let's pick up x equal to -0.1. -0.1, then the r of -0.1 is -0.1 to 4 plus 1 over -0.1 what's that square. Okay, it's going to be 1.0001. This one is a 0.0001. Power 4 zeros. So add 1 is this. Power 2 zeros. But it's a positive number, so it approaches positive infinity. Right side, let's pick up 0.1. Then you check 0.1. 0.14 to 4th power plus 1 over 0.1 squared. It's the same thing. Okay, it also approaches positive infinity. This time, they both approaches positive infinity. Very good. Now let's try to sketch. There's one more thing. This is a vertical asymptote. Because this one has no horizontal or oblique, let's try to see if it can intersect this graph, y equal to x squared. So for y equal to x squared, you set this function, this is r, equal to x squared, equal to this simple function. Then you will get x squared cancel. You get 1 over x squared is equal to 0. This has no solution. No solution means it will not intersect this parabola. Okay, so now let's try to sketch. This is a parabola. We need some starting point. For example, for 1 and -1, we get the value. When x is 1, r is 1. When x is -1, r is also 1 here. And when x approaches 0 from left side or right side, they both approach infinity. So it's this way. There's no down term because they're both past infinity. And if you let x approaches infinity to the right or to the left, it will be close to this graph. But you cannot sketch the graph here. If you sketch it here, you see if you connect it with a 1, 1, 2, you will cross this. You will cross parabola. Then you will have intersection. But this place it says there's no intersection, so your graph will be inside. Here the same thing, inside. So you try to connect them. That's it. Because this is an even function, you can examine it's an even function, so that's why it's symmetric about the y-axis. We don't have a lot of additional information, so that's the best thing we can do, right? If you get all the steps, this is the best graph we can have without additional support. Don't cross this y equal to x squared because here there's no solution. Okay? Let's do one more example. We have r of x equal to 3x squared minus 3x over x squared plus x minus 12. We need to factor it. So the numerator, we factor out 3x, we get x minus 1. Denominator, we get, what do we get? We get x plus 4, x minus 3. How do I get it? The numerator, the x squared have 1, 1. Negative 12, because here we need a 1, so we write 4 negative 3. 4 times negative 3 is negative 12. You do the cross multiplication, you get a 1, so that's exactly this form. Okay, so the step 1, domain. Domain is a set of all real numbers except x equal to negative 4 or x is 3. Step 2, it is in the lowest term. Step 3, y-intercept, x-intercept. Y-intercept r of 0. R of 0, x is 0, x is 0. The numerator is 0, so 0. X-intercept. When the numerator is 0, it doesn't matter what the denominator is. 0 over whatever number is 0. Because 0 is in the domain, denominator is definitely non-zero. X-intercept, you let r of x equal to 0. The numerator is 0. So you get 3x equal to 0, x is 0. Or x minus 1 equal to 0, x is 1. So there are two x-intercept. When you have two x-intercept, you are going to do behavior near intercepts twice. So near x equal to 0. X equal to 0 comes from 3x. So the r of x is almost this 3x. Then 0 minus 1, negative 1. 0 plus 4, 4. 0 minus 3, negative 3. So it's a 1 over 4 times x. Negatives and negatives and cancel. 33 cancel. There's only 4. So it's a straight line. And near x equal to 1, r of x x equal to 1, it comes from x minus 1. You keep this term. When x is 1, it's a 3. X is 1, that's 5. X is 1, it's negative 2. So it's negative 3 over 10 times 1 minus x. Okay, so this is a line in this direction. This one is a line in the opposite direction. Okay, and step 4, vertical asymptote. This is in the lowest term. Vertical asymptote comes from the zeros of the denominator. So x equal to negative 4, x equal to 3 are vertical asymptote. Horizontal asymptote. Horizontal asymptote, this is improper. Improper, we have to do the long division. So we divide 3x squared by x squared, got a 3. So you have r of x equal to 3 plus negative 6x plus 36 over x squared plus x minus 12. So y equal to 3 is a horizontal asymptote. This is a 3. Y equal to it. Vertical asymptote, x equal to it. Horizontal asymptote, y equal to it. And after you get the horizontal asymptote, you have to check if the horizontal asymptote intersect the graph or not. So you let this r you let this expression equal to 3. You cancel 3, you get the negative 6x plus 36 over x squared plus x minus 12 equal to 0. The numerator is 0. You get x equal to 6. Okay, so at x equal to 6, the graph of the rational function intersects this horizontal asymptote. Okay? 6. We have several points. We have what we have. We have negative 4, 3, negative 4, 3. We have 0. Oh, no, here, 0 and 1. X-intercept, 0 and 1. Y-intercept is not in the discussion. This is everything is in X. So you will have a lot of subintervals. 1, 2, 3, 4, 5. We will have 5 subintervals. And then we pick up the sample point from each subinterval and determine the value. So here we pick up negative 5. Here we possibly will pick up negative 2. Here we pick up 1/2. This place we pick up 2. And on the right side we pick up 4. So you evaluate r of negative 5 in the original function here, in this function. You evaluate, you let x be negative 5 and do the computation. You will get it's a 11.25. At negative 2, you will get r of a negative 2 is negative 1.8. R of a 1/2, you do the computation, it will be 1 over 15. And r of a 2, it will be negative 1. And r of a 4 is 4.5. So just do the computation. I just copied it from the textbook, but you have to do the computation in order to get the correct number. Okay, so positive above x-axis, negative below the x-axis. This is above, below, above. Okay, so that's our case. And then we are going to study the behavior close to the asymptotes. Okay, so it's close to the asymptote. You have 2 vertical asymptote. X equal to, where is the vertical asymptote? Negative 4. X equal to negative 4. Let me copy the function here. 3x squared minus 3x over x squared plus x minus 12. Well, in this part, you are going to study the left part, right part. How do you do that? The left part, you pick up x equal to negative 4.01. It's negative. Left part is negative 4.01. Right part, you pick up a negative 3.99. Well, it's bad because you have such complex expression. You have to really do some computation. After you do some computation, you will see that on the left part, it will approach positive infinity. On the right part, it will approach negative infinity at a negative 1, negative 4. And positive 3, you do the similar discussion. You have the left, you have the right part, and the 3, left part, you choose x equal to 2.9, and right part, x is choose 3.1. You do the computation here. You can choose a simple one, not such complex. But still, it's just very tedious. It's not interesting at all. Okay, so you pick up them and try to determine that. You will see on the left part it's negative infinity, the right part is positive infinity. Just do it by hand. It will be painful, but we have to do it. Okay, so let's check. Horizontal asymptote. Horizontal asymptote is y equal to 3. Did I? Okay, I mentioned it. Y equal to 3 is a horizontal asymptote. And you check here, only at x equal to 6, the graph intersect the horizontal asymptote. So we will keep this in mind. Only at x equal to 6, you will have intersection. Which intersects the graph at x equal to 6. Okay, this is an important property. Let's try to sketch. Okay, this time it will be very difficult. So many steps. Negative 4, positive 3. And you have 0, you have 1, 0, 1, that's an intersection. X-intercept, okay, and 3 is here, y equal to 3. We did this computation. We know that at negative 5, we evaluate it is equal to 11.25. So at negative 5, it's 11.25, it's here. And we also know that on the left side of negative 4, it approaches positive infinity. It approaches positive infinity. And when x approaches negative infinity, it will approach to this horizontal asymptote. But you cannot cross it, because if you cross it, you will have intersection. But this place, there's no intersection. So you can only sketch it above the horizontal asymptote on the left part. Okay, so that's the best way. And for the vertical asymptote on the right side, it's a negative infinity. Here's a negative infinity. This is the left side. On the right side of 3 is a positive infinity, this way. And when it is equal to 6, you have intersection. You have intersection, then you will cross it, okay? And this part, you have 0, 0. And between 0 and 1, you see here, between 0 and 1, it's a 1 over 15, it's above x-axis. Below, on these two parts, it's below the x-axis, okay? That's what we get in step 6. So it has to be this way. Okay, and this part, it approaches positive infinity, and it crosses the x-axis. After it crosses it, you cannot draw it back because there's no second intersection point. And it will approach to horizontal asymptote, so you have to make it close or very flat. Okay, so this is the idea. You see here, we actually consider all the information we just found in the previous steps. We have vertical asymptote, horizontal asymptote. We know where it intersected the horizontal asymptote, when it is positive, when it is negative, and it goes to negative infinity or it goes to positive infinity. And for this part, I skip the computation because of the computation x squared, it's just very long, okay? But you just plug in the number and determine the sign. You don't need the concrete value, you just need to sign. I need the sign. You have this x, you check r of 2.9. R of 2.9, you check this value. This value is negative, it will give you negative infinity. And here, you check the value r of 3.1. If you get a positive value, then you will get positive infinity. Okay? Okay, so this is the graph. And we will continue more graphs in next videos. Okay? So we'll stop this video and continue next one. Thank you.